Welcome to Global Trends. Please subscribe and hit the bell icon for more breaking updates. Deep beneath the tranquil landscape of the Swiss-French border, where rolling hills meet cutting-edge science, lies a marvel of human ingenuity. Here, CERN operates the Large Hadron Collider, a sprawling underground ring stretching for 27 kilometers, connecting nations and minds in the pursuit of knowledge. This is the most powerful scientific instrument ever constructed, capable of recreating conditions just moments after the Big Bang. Recently, headlines around the world have claimed that CERN has activated a mysterious neutrino quantum field, stirring both excitement and anxiety among the public. These reports have sparked global awe and apprehension, as people wonder what new frontiers might be crossed, or what dangers might be unleashed. In truth, CERN has embarked on a series of sophisticated experiments, pushing the boundaries of technology to probe the elusive neutrino with unprecedented precision and care. This process is far from simply flipping a switch. It's a delicate orchestration, involving intricate detectors and finely tuned particle beams, all designed to listen for the universe's faintest whispers. The LHC, once famous for its monumental particle collisions, now turns its focus to the subtle, ghostly neutrinos, particles that rarely interact with anything at all. These new experiments aim to study these nearly invisible particles, shifting attention from the thunderous bangs of the past to the faintest echoes of the cosmos. By venturing into this uncharted territory, scientists hope to confirm wild theories about the universe, or perhaps stumble upon phenomena that defy imagination and rewrite the laws of physics. The stage is set for discovery, and the scientific community waits with bated breath, eager to witness what secrets the universe is finally ready to reveal. To truly appreciate CERN's latest scientific pursuits, we first need to unravel the mystery of the neutrino, a particle so elusive it's often called the ghost particle. Despite being one of the most abundant particles in the universe, neutrinos are incredibly difficult to detect, slipping through ordinary matter almost as if it isn't there at all. Every second, trillions of neutrinos pass through your body, streaming from the sun and other cosmic sources, yet you never feel them. They interact so rarely with matter that they can travel through entire planets without leaving a trace. This makes them both fascinating and frustrating for physicists, who have spent decades trying to catch and study these fleeting visitors from the universe. Neutrinos are born in the heart of stars during radioactive decay and in powerful nuclear reactions. They come in three distinct types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor is associated with a different charge particle, and together they form a trio that is fundamental to our understanding of the subatomic world. What makes neutrinos even more intriguing is their ability to change from one flavor to another as they travel through space. This phenomenon, known as neutrino oscillation, was a groundbreaking discovery. It revealed that neutrinos must have mass, overturning long-held assumptions in physics. The Standard Model of Particle Physics, our best theory for describing the fundamental particles and forces, originally assumed neutrinos were massless. The discovery of their mass was a major crack in this model, hinting at new physics waiting to be uncovered. The fact that neutrinos have mass suggests there are deeper layers to the universe than we currently understand. Physicists now believe that studying neutrinos could open the door to a more complete theory of nature, one that goes beyond the Standard Model and answers some of the biggest mysteries in science. Neutrinos might even hold the key to understanding why the universe is made of matter, instead of being a void filled with equal parts matter and antimatter. This question sits at the heart of cosmology and has puzzled scientists for generations. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter which would have annihilated each other, leaving behind nothing but energy. Yet somehow, matter won out, and the universe as we know it exists. One possible explanation is that neutrinos and their antimatter counterparts, antineutrinos, behave just a little bit differently. This tiny difference, or asymmetry, could have tipped the cosmic balance in favor of matter, allowing galaxies, stars, and life itself to form. If this subtle asymmetry is confirmed, it would explain why the universe is filled with galaxies, stars, planets, and ultimately why we exist to ask these questions. In the end, the humble neutrino, once thought to be insignificant, might turn out to be the hero of our cosmic story, holding answers to the deepest mysteries of existence. LHC detectors focused on heavy particles like the Higgs boson, missing high-energy neutrinos. CERN's phaser and SND at LHC experiments now stand in the path of these particles. FACER, a compact design, catches weakly interacting particles missed by other detectors. In 2022, FACER detected neutrinos from a collider, opening new study methods. SND at LHC distinguishes neutrino flavors and studies their interactions. These experiments measure neutrino interaction strength at unprecedented energies. Any deviation from the standard model could signal new physics. They're also searching for hypothetical particles, potential dark matter candidates. FACER and SND at LHC chart new territory, possibly hiding new particles and forces. The LHC generates a digital tsunami of data, overwhelming conventional computers. AI, particularly machine learning, is crucial for sifting through this data. AI algorithms recognize particle decay signatures amidst collision debris. They help reconstruct particle trajectories and classify events with speed and accuracy. AI acts as an intelligent filter, enhancing our ability to find new physics. CERN is integrating quantum AI, using quantum mechanics for complex calculations. Quantum AI could simulate particle interactions with unprecedented detail. This synergy between particle physics and quantum computing accelerates discovery. As experiments become more sensitive, our ability to interpret findings grows. DUNE, a colossal experiment, promises to push neutrino study into a new realm. It will fire a neutrino beam from Chicago to a detector in South Dakota. DUNE aims to study neutrino oscillations and CP violation, key to matter's dominance. The detector will provide a clear picture of neutrino transformations. DUNE also searches for hidden dimensions, proposed by theories like string theory. Neutrinos might take shortcuts through these dimensions, altering oscillation patterns. Discovering extra dimensions would profoundly change our perception of reality. The Standard Model is a triumph of modern physics, elegantly describing the fundamental particles and forces that make up our universe. It has allowed scientists to predict and discover new particles, and its equations have stood the test of time in countless experiments. But despite its success, the Standard Model is incomplete. It remains silent on some of the universe's most profound mysteries, such as the nature of gravity, the elusive dark matter that makes up most of the universe's mass, and the enigmatic dark energy that drives its accelerating expansion. Neutrinos, once thought to be massless and barely interacting, have surprised physicists with their ability to change flavors, a phenomenon known as neutrino oscillation. This discovery proved that neutrinos have mass, a fact the Standard Model cannot fully explain. Because of this, neutrinos have become a window into physics beyond the Standard Model, offering clues about what lies outside our current understanding. Their strange properties and unexpected behaviors could reveal more cracks in the model's facade, hinting at new physics waiting to be discovered. Some bold theories even predict entirely new phenomena associated with neutrinos, such as the existence of a hypothetical sterile neutrino, a particle that could interact only through gravity and not the other fundamental forces. If such a particle exists, it could help explain the mystery of dark matter. Experiments like FACER and SND at LHC at CERN are designed to search for these hidden particles, while the ambitious DUNE project aims to capture and study neutrinos in unprecedented detail, hoping to find evidence of new particles and forces. In this way, neutrinos are not just passive bystanders, they are crucial guides, leading us toward answers to the universe's biggest mysteries, from the origin of mass to the fate of the cosmos itself. By studying neutrinos, scientists hope to open a unique portal to a more complete and unified theory of physics, one that could finally connect the known with the unknown. Neutrinos are no longer just a curiosity for physicists, they have become central to our quest to understand the universe at its deepest level. In the search for answers to the cosmos, neutrinos may truly hold the key. The physics community is excited and apprehensive about new experiments. These experiments could discover new particles, dimensions, or solve matter-antimatter asymmetry. Such discoveries would rewrite textbooks and redefine our place in the cosmos. The worry is about the upheaval a major discovery would bring. A discovery shattering the Standard Model would be intellectually earth-shaking. There's also concern about finding nothing, confirming the Standard Model with higher precision. This would leave us with the same mysteries but fewer clues. Whatever the outcome, we're in a pivotal moment for science. The journey has begun, and we're ready to listen to the cosmos's whispers.